everyone. Today we're going to be going through the question 7 to question 10 of the January 2013 paper 2 for further pure maths. I realize it's been a long time since I made a video. Someone made a request for this specific paper, and I'm not going to try to pronounce their name, but you know who you are if you're watching this video. So the reason I'm making the end half first is that it's more likely that people will need help with this than on the first half, because I have a limited time in which to make these. Anyway, so we're going to start with this question, which is a 11-mark question about the Cartesian Coordinate Plane. So, how do we approach this? The line L passes through the points with coordinates 1, 6, and 3, 2. Show that the equation of L is y plus 2x equals 8. Okay, so one thing I wanted to put out is that I found a very neat shortcut for getting the equation of a line if you have two of the points. So you may be familiar with the equation for the gradient. M is y2 minus y1 over x2 minus x1, which would still hold true, so it would be 2 minus 6 over 3 minus 1. And at this point, what we can do here is we can let the equation of the line, if we just want to look at one of the 2 points, such as 1, 6, we let the equation of the line be that gradient, which is m is equal to y minus y1 over x minus x1. And this y and x, I do not mean it to be a specific value of y or x, but it's just y or x in general, because we know that in order to calculate the gradient from that point to our point 1, 6, this equation will have to be true. So we can actually use this as a kind of equation for our line. So minus 2 is equal to y minus, well, y1 would be 6 over x minus x1, so x minus 1. And multiplying both sides by x minus 1, we get minus 2 x minus 1 is equal to y minus 6. And if we flip the equation around and we add 6 to both sides, we get y is minus 2 x minus 1 plus 6. Or rather, if we want to expand this bracket, y is equal to minus 2x plus 2 plus 6. Y is minus 2x plus 8. Y plus 2x is equal to 8. So we have shown that the line through these 2 points is equal to y plus 2x equals 8. And you may want to make clear that this is the gradient and that this is the equation of the line you're working with. So once you have this, what are we doing now? The curve C has equation xy equals 8. Show that L is a tangent to C. Okay, so to show that L is a tangent to C, you would first want to show that the point they intersect, at the point they intersect, they have the same gradient. So if xy is equal to 8, then y is 8 over x, or 8x to the power of negative 1, which will be clear why I'm doing this, because we're going to differentiate it. dy over dx is minus 8x to the negative 2. So what are we doing now? We want to see the point of intersection between x over 8 and between 8 over x, and 8 minus 2x. So once we know this, given that y is equal to, or y1, a specific value of y, would be equal to 8 minus 2x is equal to, or this might not be necessary as we're just trying to make the two lines equal to each other to see which x it is. 8 minus 2x is equal to 8 over x. We multiply everything by x to get 8x minus 2x squared equals 8. We add everything to one side. 0 is 2x squared minus 8x minus 8, or is x squared minus 4x minus 4. Plus 8 actually, plus 4. And you may find this to be a pattern you've seen before, because this is actually x minus 2 squared. So, in fact, because this is squared, it actually tells us immediately that this is a tangent. The differentiation here was unnecessary. Because if you think about it this way, if you are moving everything to one side of the equation, it's like flattening the function down to seeing whether it's tangent to the x-axis, the horizontal line. And as you know, for example, if you have a quadratic or a polynomial with a repeated root, it means it's tangent to the x-axis. It's a root that doesn't cross the x-axis. So when you split the equations back out, you will still get a tangent. So given that this factor is a square, it's a factor that appears multiple times, you can say it's a tangent. So what next? Given that L is the tangent to C at the point A, find the coordinates of A. Okay, well that should be trivial because we already know that 0 is equal to x minus 2 squared here. So 0 is equal to x minus 2, x is 2, that's the x coordinate. And if xy equals 8, then that means 2y equals 8 and y equals 4. So the coordinates of the point A are 2, 4. And finally, find an equation with integer coefficients of the normal to C at A. Well, following on from my previous trick with this m is equal to y minus y1 over x minus x1, what you do, because the normal is the line which is perpendicular at that point, and we already know the gradient of the tangent, m, is -2, then the gradient of the normal would be minus 1 over m, which would be minus 1 over minus 2, or just positive 1/2. So what we can do here is, in a very similar fashion to how we found the tangent the first time, we let half, being the gradient, be equal to y minus y1, where y1 is a coordinate that we know and y is the variable, over x minus x1 in the same fashion. So 1 over 2 is equal to, and we are trying to find the normal to C at A, so A being 2, 4, our x1 is 2 and our y1 is 4, so it'd be y minus 4 over x minus 2, and multiplying both sides by 2, and we get 1 is equal to 2y minus 8 over x minus 2, and then multiply both sides by x minus 2, you get x minus 2 is 2y minus 8. And fancy that, this is already an integer coefficient. We can move everything to one side, and we get 2y minus 6 minus x. Or it would be nicer phrased as 2y minus x minus 6 is equal to 0. Because we're adding 2 here, we're adding 2 to both sides here, and we're subtracting x from both sides here. So that's our equation of the tangent line, the normal line, sorry. Alright, I'm going to note down the time at which this question was finished. Of course, one thing to note is that I've had a lot more opportunity to learn math and stuff since the last time I was doing these further pure videos, because when I was doing them before, I was actually sitting the exam in the same year as you guys. But now I'm like, have done more, so these may be faster, and always pause and make sure you understand something before you go on. Like, you can watch it at good, like 1x speed, even though the normal speed is normally a lot too boring for most people. If you can't make sense of something, watch it happen slower. And if you have questions, put it in the comments and I will explain. Right, now let's move on to question 8. I realize the m is y minus y1 over x minus x1 thing is also a new technique, and I kind of want to make a video on this anyway because it's extremely useful. Because if you don't need to give stuff in a standard form like this, then you can even give your answers in the sense that the line equation is y minus y1 is mx minus x1, and that's literally just your answer right there. Okay, so now we head on to question 8, which is to do with vectors. In figure 3, OA is A, OB is B, and M is the midpoint of AB. The point P is on OA such that OP to PA is 3 to 2. So this would be 3 over 5A, this would be 2 over 5A. The point X lies on OB produced, so X would be a bit more than B. So let's say from here to here is a variable we don't know, like lambda B. Find as simplified expressions in terms of A and B. Firstly, AB. So if we're going from A to B, it is the same as going backwards through OA. So going backwards from A to O is minus A. And then we're here and we want to go to B, so forwards from O to B is plus the vector B. Secondly, OM is going from O to A and then going halfway from A to B. So what we can actually phrase this as is A plus a half AB. And actually we should make this clear that this is AB being equal to this. And then we substitute negative A plus B into this. So the vector A plus minus a half A plus a half B. For OM, and finally a half A plus a half B. So that's our answer for OM, because what we've done is we know that we're going from O to A first, and then halfway from A to B. If this whole vector is the one we just calculated, AB, we can use that result to find O to A to M, which is equivalent to OM. So now what do we do? PM, that's what we're trying to find. In a similar fashion, because PA is 2 over 5A, and we can phrase this as 2 over 2 plus 3A, or in fact, it would make more sense to the examiner if we showed our thought process. PM is PA plus AM. That's the first step. And this is equal to 2 over 2 plus 3 OA, because of the ratio that was mentioned at the beginning of the question, and plus a half times AB, because of the fact that M is the midpoint between A and B. So this is 2 over 5A plus a half times minus A plus B, because we're substituting in our result for the vector AB from earlier. And adding it all up, you get 2 over 5 plus minus a half is minus a tenth. So minus 1 over 10A plus a half B. So this part seemed to have been fairly straightforward. Given that P, M, and X are collinear, find in terms of B, O, X. So if we know that P, M, and X are collinear, that means they're all on one line. That's the meaning of collinear. And that also means that if we have the vector here, Pm, there's the one unknown lambda, which is from OB to X. But we also know that Pm plus this extra bit we'll call mu Pm, where this character, mu, is an unknown scalar that we want to find out. It says find OX in terms of B. So we want to find the value of 1 plus lambda. So what we will first do is write out all the knowledge that we have already. So Px, OP plus PM plus MX is equal to OB plus BX. That's the first train of thought I'm getting. OP plus PM plus MX is equal to OB plus BX. And the reason I put this out is because they both of these journeys start and finish in the same place. So it goes from O to P to M to X, and also O to B to X. And these two journeys are equivalent, so we put them in the equation with each other. And then now we express all of these in terms of A and B, because once we have some expression A plus some expression B is equal to a similar looking thing on the other side, then because of how vectors work, these two will always be equivalent and independent of these two, which will always be equivalent. That's a key problem-solving step that you should remember, because it tends to be in these questions that they're trying to get you to form a simultaneous equation with these and these. So we know that OP is 3 over 5A, and we calculated earlier that PM is minus 1 over 10A plus 1 over 2B. And now MX, we have labeled it mu PM, but we need to make clear to the examiner that's what we're doing, so let MX equals mu PM because of collinearity. Then we get this same vector again, but multiplied by mu. So minus 1 over 10 mu A, we're adding in mx now, plus 1 over 2 mu B. And finally, this is equal to OB, which is just the vector B, plus BX, where BX is lambda b. So again, we want to make that clear. Let bx be equal to lambda ob. Now we want to get our equation into this form, where we have some expression multiplied by a plus some expression multiplied by b is equal to the same on the other side. So obviously on this side it is much easier. We know that 1 plus lambda times the vector b plus 0 times the vector a will be equal to, on this side, let's look at the a's first. 3 over 5 minus 1 over 10 is a half. And then that is also minus 1 over 10 mu. So a half minus 1 over 10 mu times the vector a plus, and now let's look at the b vector component, plus a half plus a half mu times b. So that's what our b will be. Is equal to the expression we just worked out on the right-hand side. So from this, we can get two simultaneous equations. Firstly, that looking at just the a vector, a half minus 1 over 10 mu is equal to 0. And because these are the coefficients of the a vector on each side of the equation. And secondly, that a half plus a half mu is equal to 1 plus lambda. So what do we do now? Of course, the first equation is easier to solve because it has one variable. So let's solve that one first. 1/2 is 1/10 mu, and multiplying both sides by 10, 5 is equal to mu. And now substituting this into equation 2, we get that a half plus a half times 5, which is the value of mu, is equal to 1 plus lambda. Or in fact, 1 plus lambda is equal to 3. And because we are looking for OX, the entire length, O to B plus B to X, which is 1 plus lambda times B, we can go directly from this result to saying that OX is equal to 3B. And that's this part of the question complete. Finally, we must find the ratio, the area of OAM to the area of OAX. So, this ought to be very interesting. I haven't actually had much experience with these kinds of area questions, but it should be very interesting. So, we should think about how to attack the problem. One thing that we could do is use the fact that they have a common side, but I doubt that it will be relevant simply because the common side does not have anything else that we can use as, for example, a height. So, what is another thing that we could do? Well, we know that this length, AM, and this length, MB is the same. And I'm wondering if we can try and get the height of some of these triangles to come into play here, but I'm really not sure if that is feasible, because one area should be able to be found in terms of the other in this kind of question. I am quite sure that the area of OAM and OMB are equal. This triangle here and this triangle here, from OAM and OMB, these two triangles ought to be equal because AM and MB are the base lengths, and they have the same height because they end up at the same vertex O. So that probably comes into it at some point. Though I'm still quite confused about what else we could do. We're looking for OAX. This area here, this entire big triangle. Then in this case, because we know that px is 1 plus mu times pm, and because that this just keeps going in the same direction, pm must be proportional to the height, then actually let's write this argument down logically. One of the coolest thing about further pure is that the examiners will take your answer as long as it makes sense, as long as it's a valid logical argument. Okay, so let the base of both triangles be OA. That's the first step. And let the height of both of these triangles be the altitude from M and the altitude from X respectively to OA. The altitude, in fact, is the line that drops down from M at right angles to the line of OA. And that would be the height. So we're going to call the foot of the altitude M prime, as well as X prime here. So X prime and M prime will be our heights. Altitudes from M and X to OA respectively. M prime and X prime. So what is the next step of our logical argument? I've sort of worded it out already in speech, but we need to get it onto the paper. M prime ought to be in the ratio of 1 to mu with X prime, because originating from P, because of the line PMX, we can use the ratio of PM to MX, or PM to PX being equal to MM to XX, or the fact that PM prime M and PX prime X are similar triangles. That might actually be a better way to put it. So, PM prime M is a similar shape to PX prime X, And because Pm to Px is 1 to 1 plus mu, this means Px, or actually this means in the same way, mm prime to xx prime equals 1 to 1 plus mu. Or because mu is 5 equals 1 to 6. Since the bases are equal, and the heights are in the ratio 1 to 6, we can, it follows that the area OAX is 6 times the area OAM. So that is how we reach this logical conclusion. C is the kind of question where you will probably need to write out multiple sentences in order to logically prove your case. Math is a problem-solving environment. It doesn't necessarily always have to be equations. It is sometimes best to write it out in English as well. Alright, so given that this question has been done, I will move on to question 9. Again, if there are any questions, do not hesitate to put it in the comments. Goodness, okay, so this is a question about series. I am more confident with series than I am with vectors, to be honest, because vectors is something that I haven't done in a while, but I'm still quite happy with how I answered that question. The third and fifth terms of a geometric series S are 48 and 768 respectively. Find the two possible values of the common ratio of S. Okay, so one thing we can do quickly is we know that the terminology of each term, let it be U3 and U5 being the third and fifth terms. So U3 is equal to 48 is equal to U1 R squared, and U5 is equal to 768 is equal to U1 R to the power of 4. So U1 R to the 4 over U1 R to the 2 is equal to R squared is equal to 768 over 48 is equal to, let's get a calculator in here. So it follows from this that if R squared is equal to 16, then the two possible values of R are positive 4 and minus 4. Now what do? We want to find the first term of S, given that U1 R squared over R squared is going to equal the first term U1. We can say that 48, which we know is U1 R squared, over R squared, which is 16, is equal to 3, which is U1. So that's the first term. Given that the sum of the first 5 terms of S is 615, find the sum of the first 9 terms of S. Alright, so something to note here. There is a logical shortcut that we can take. Imagine you have the sum from 1 to 5 is equal to 615. So that means the sum from 2 to 5 is equal to 615 minus the first term, which is 612. So why is this useful to us? Well, if we want to look at U2 through U5 compared to U6 through U9, U2 to U5 is U1R plus U1R squared plus U1RQ plus U1R4. But also, U6 to U9 would be U1R to the 5th plus U1R to the 6th plus plus U1R to the 8th. And what can we actually do here? We can factorize R to the 4 out, because the sum from 6 to 9 would be R to the 4 times U1R plus U1R squared plus plus U1R to the 4th. And this is actually, you guessed it, it's the sum from 2 to 5. So because of this, the sum from 6 to 9 is R squared times, or R to the 4 times the sum from 2 to 5, or 256 times the sum from 2 to 5, which is 612. This works out to be 156,672. And what we can do here now is that the sum from 1 to 9 is equal to the sum of the first term plus the sum from 2 to 5 plus the sum from 6 to 9, or the first term just being 3 plus the sum from 2 to 5, 612, plus the sum from 6 to 9, which is this number here. You put that all in the calculator to sum up. And you get your final answer for the sum to 9 terms, 157,287. I really like that question. That was a pretty neat solution. Okay, so what do we do now? Another geometric series T has the same first term as S. The common ratio of T is 1 over R, where R is one of the values obtained in part A. The nth term of T is Tn. Okay, so if T2 is greater than T3, if 1 over R is equal to, or this being their common ratio, if 1 over R is equal to minus 1 over 4, and T3 is minus 1 over 4 T2, in that case, you would get something like, because T1 is 3, T2 would be minus 3 over 4, and T3 would be positive 3 over 16. And now let's see what's the condition they gave us. T2 is greater than T3, so it is not the case. This must mean that 1 over R is positive 1 over 4. So the common ratio of T of series T is equal to positive 1 over 4. Now what do we do here? The sum of the first n terms of t is tn. Writing down all the numbers on your calculator display, find t9. Alright, so this is just simply using the formula that you learned for the finite sum of a geometric series. That is, the sum to n terms is equal to the first term g times 1 minus r to the power of n over 1 minus r. Well, n is the number of terms and r is the common ratio, is equal to 3 times 1 minus 1 over 4 to the power of 9 divided by 1 minus 1 over 4. And now we're just going to put this in the calculator and write out all the numbers we get. It is much simpler than the parts of this question so far, to be honest. Yep, so we get a sum that's very close to the number 4. I predict that's what they're going to ask us to do next. It's equal to 3.999984741. That's all the digits on our display. Right, next question, find the infinite series. Oh, never mind. The sum to infinity of t is t infinity. Given that t infinity minus tn is greater than 0.0002002, find the greatest value of n. Okay, this is a really interesting question actually. Alright, so what do we do here? Find the greatest value of n. This should be very interesting. We already know by inspection of the result from E, t infinity is equal to 4, because this is so close to 4 that it's unlikely to be anything else. What we can do is actually express both of these algebraically. So for example, g over 1 minus r minus g to the 1 minus r to the n over 1 minus r. This being t infinity, this being tn, is greater than 0.002. And if 1 minus r is 1 minus 1 over 4, which is 3 over 4, multiplying both sides by 3/4 gets us g minus g 1 minus r to the n must be greater than 0.002 times 3 over 4 is 0.0015. And we can factorize g out as well, actually. So g 1 minus 1 plus r to the n is greater than 0.0015. So as you can imagine, the next step would be to be dividing both sides by g. Because g is 3, and 3 times r to the n, which is the difference here, because we factorize g out, this minus sign multiplies by the minus sign here to get a positive r to the n, and to subtract the 1 from the 1 that we already had. 3 times r to the n is greater than 0.0015, or r to the n is greater than 0.0005, because we divided both sides by 3. And we know we can substitute 1 over 4 into r to the n is greater than 0.0005. So if we take the natural log of both sides, because as far as I recall, the Further Up Your Exam Board prefers that you do this instead of explicitly taking the log with a base of something, though it should be absolutely fine if you decide to do that as well. I'm just going to do this for clarity. You take the ln of both sides, so n times the natural log of 1 over 4 is greater than natural log of 0.0005, and we divide both sides by ln of 1 over 4. And remember to flip this sign. Flip the greater than or less than sign. Flip it, because natural log of, or log of anything that is less than 1 is going to be negative. So n is less than ln 0.0005 divided by ln 1 over 4. Cool! So we just bang this into the calculator, and we'll have our answer for n, or rather a limit of n that we need to find the lowest integer beneath. N is less than, I'm quite surprised actually, 2.0604. This seems a little small. This really does seem a little small. I'm wondering if I've got anything wrong here. Ah, yes, no, never mind. It was a calculator mistype. N is less than 5.48289, so on. So n is equal to 5 is the highest integer for which the condition is still true. You can think about it another way. Say you were to plot the function of the sum on a graph, and you'd have your asymptote at 4, and the sum would keep climbing up. It's trying to say, when's the cutoff point? When the sum is 0.002 away from the infinity sum. And this would keep getting smaller by, say, a quarter each time. Or 3/4, in fact. Anyway, yeah, this seems very interesting. I'm quite satisfied with this question as well. Again, if you have any questions, put them in the comments. Now we will move on to the final question, which I looked ahead. It is a log equations question. So, funny thing about this paper is that question 10 is actually not the most intense question on the paper. There's also question 3, I think, at the beginning is also quite intense. So if at the person who told me to make this, requested me to make this video, if question 3 was the one you needed help with, I apologize for doing this part first. So solve these equations, these log equations. Alright, so question 10a, what can we have here? Log x of 10 to the 24 is 5. So ln 10 to the 24 over ln x is equal to 5. Now we can flip the 5 in the ln x, so divide by 5 and multiply by ln x on both sides to get ln 1024 over ln, or just over 5 is equal to ln x, and 5 is equal to ln e to the 5, if that makes sense, right? And also ln 1024, we can simplify it to 10 ln 2, or this would be 5 ln e. So if this is 10 ln 2 over 5 is equal to ln x, we can cancel this fraction here to get 2 ln 2 is equal to ln x, or ln 4 is ln x. And finally, raising both sides to the power of to be a power of e, we get x is equal to 4. Alright, so that one's quite straightforward. Now let's handle this. Log 5, 6y plus 11 is 3. Alright, so b. Log 5, 6y plus 11 is 3. I think the direct thing to do is to just raise both of the sides to be a power of 5. So 5 to the log 5, 6y plus 11 is equal to 5 to the power of 3. And in this case, 6y plus 11 is 125. And yes, it becomes trivial from here. It's just a linear equation. So subtract 11 from both sides, you get 114, and then divide both sides by 6. You get, this is 90 plus 24, so this becomes 4, and this becomes 15, makes 19. Y is 19. Cool. So we've solved that equation. Now it's just C, the 6 mark one. 2 log 3t plus log t 9 is 5. Alright, what we can do here, because 9 is because 9 is 3 squared, and we have 3 here and a 2 here, my intuition jumps to me to rephrase this term as 2 log t 3. I feel like that's going to be useful. And anyway, you can divide both sides by 2 if we feel the need to. So let's start on a fresh page. We have the luxury of space here. 2 log 3t plus log t9 is 5. 2 log 3t plus log t9 is 5. Rephrasing the second term like I suggested earlier, we get 2 log 3t plus 2 log t3 is equal to 5. In this case, log 3t plus log t3 is 5 over 2, dividing every side by 2. So what do we do now? We can express these as in terms of ln. So ln t over ln 3 plus ln 3 over ln t is 5 over 2. So what do we do here? This, although it may not look like it, is actually a quadratic in disguise. I'm going to explain how. If you ever get an equation where the base and the number inside the input of the log function are swapped around in different terms, it is secretly a quadratic. So we're going to let x be equal to ln t over ln 3. Because ln 3, the constant, we want that to be on the bottom so it's more simple to calculate later. Let x equal that. Now, ln t over ln 3, that's x, plus ln 3 over ln t, that's the reciprocal. And what's the reciprocal of x is 1 over x. And then 5 over 2, it's not related to x at all. It's our constant term. Wow, that's crazy. A quadratic out of nowhere. What can we do now? We multiply every side by, or we multiply both sides by x, so that every term gets up 1 degree, and we have an actual quadratic. So x squared plus 1 is equal to 5 over 2x. And we move that back around here. X squared minus 5 over 2x plus 1 is equal to 0. And in fact, we can just use the quadratic formula because this is a fractional thing. It's kind of ugly. I'm going to multiply it by 2. 2x squared minus 5x plus 2 is equal to 0. Oh, and now that I've done that, a solution has jumped out at me. So you know how when you are factoring by grouping, A, B, the two numbers you need to group into being A and B, they multiply to the unit coefficient times the x squared coefficient. So AB is 2 times 2 is 4, and A plus B is minus 5, and this leads me to believe that A and B are minus 4 and minus 1. So it turns out we didn't need to use the quadratic formula after all. 2x squared minus 4x minus x plus 2 is equal to 0, and factoring out 2x from both sides here, x minus 2, 2x, x minus 2, then minus 1, x minus 2 is equal to 0. 2x minus 1, x minus 2 is 0. And we will get x is equal to 1 over 2 and 2. But we're not done. We need to substitute this back in order to find t. So ln t over ln 3 is equal to 1 over 2, 2. ln t is equal to half ln 3 and 2 ln 3. And if we use the log rule that if you have a constant multiplied by a logarithm is equal to the logarithm of whatever input to the power of the constant, this will make more sense when I write it down. We can change this into ln root 3 and ln 9, 3 squared, 3 to the power of 1/2. So ln t is equal to those, and we raise everything to be a power of e, and we get t is root 3 or 9. Excellent stuff. And that would be how you solve question C. If there are any errors in this video, please don't hesitate to comment. If you found this helpful, share it with your classmates. Strive for success, and thank you for watching.